Okay. Next question. Sinusoidal voltage source, blah blah blah. They give us some values, and then these devices determine which components are parallel, which are in series. So I think it's very obvious to see who is parallel, who is series. This is parallel to this, is parallel to this, is parallel to this one. Yeah. Okay. So these are parallel to each other. C1 parallel to L, it's parallel to C2, it's parallel to RL. Okay, so these are all parallel to each other. And you can say that R is parallel to all of them as well, right? This is in fact parallel to each other. And also VS is parallel to this whole thing. Oops. Okay, but you cannot put VS over here. This relationship means parallel to each other. But look at this. VS and R, they're not parallel to each other. They're in series with each other. So you cannot include VS over here. So technically, if you want to be correct, it's more correct to do this. Because VS is also parallel to all of these devices that are highlighted green, right? This is parallel to all of these. And then separately, R is also parallel to all of these. But to answer the next question, VS and R are in series with each other because they're connected end to end. If you want to use the hand to hand analogy, so this is the hand of R and this is the hands of S. See, they're only holding hands by one hand only, not both hands together. Okay, so that's how you show the relationship. Determine the natural frequency of the voltage source. So we're given that omega is 102 pi. So 2 pi f. This is 102 pi. 2 pi is over here. You can cancel the pi's. 102 divided by this is 51 hertz. Okay. Using the numerical values provided, determine the complex values of the total impedance seen by the voltage source. So we know that these are all parallel to each other. So let us find this. Let us call this Z para. Okay. So let me bring this down here. Well, let me reshare my screen because I get paranoid. Okay, yes. So we'll call this whole thing Z para. Okay. But let's find the impedance of each device first. Okay. I think that will make life a bit easier. So the impedance of Z1 is given by 1 over J omega L. Sorry, 1 over J omega C and C1. So this is 102 pi that they told us. C1 is what? 50 microfarads. I hope ZC2 is the same. Yes, ZC2 is the same. Okay, so this will also give us the value of ZC2, right? I'm not crazy. Yes, 50 and 50. Okay, so that kills two birds with one stone. So ZC1 equals to ZC2. I'm gonna calculate this value. Oh, thank heavens they're the same. So 1 over this times 102 pi multiplied by 50 microfarads. This gives about that. And then now let's find Z of L. So Z of L is given by J omega L, which is given by J times 102 pi. 102 pi times what's the 200 microhenries. 200 microhenries is equals to, sorry, J times omega times L to, this should be 0.064 J. And then lastly, we have ZC. Okay, ZC1 is done. ZL, ZC. Okay, and of course, Z of RL is just the resistance itself, which is 2. Okay, so to find Z para, we use this formula, Z para equals to 1 over ZC1, which is this, plus 1 over ZL, which is this, plus 1 over ZC2, which is the same as ZC1, plus 1 over 1 over 2. Okay, so now you solve, you punch in this value. Okay, I'm gonna straight away solve for Z para. Okay. Okay, so Z para is this 00206 plus something like that. Okay, but we're not done yet. So we found the impedance, which is Z para of this. So to find the total impedance, we had to take R plus Z para, right? Because R and Z para are the same. I mean, are in series. So let us simplify our circuit diagram. If we simplify it, this is the source, this is R, and then this is Z para. So you see, R is in series with Z para. So to find the total impedance, Z total, sorry. So to find the total impedance, you just take R plus Z para. What's the value of R? 1. And Z para we got earlier is this. So the total will be 1.00 plus 0.064 J. So this is your Z total. Okay. I am not gonna go through C because this is just a menial math task, okay? You can do it DIY and check against your peers. Determine the phasor of the current in the resistor R. So what they want is the phasor of this. So I of the R. So how are you gonna do this? So actually the I through R, right, is also the I through Z para. Okay, let's okay. Following the simplified diagram, which is this. See, the I through R is the same as the I through Z para because they're in series. So what we need to do is we find the total current through the system. So what we need to do is use V of the source is equal to I the I that we're interested in, so I of R multiplied by Z total. So I of R is given by Vs over Z total, and now we can sub in the values. So you see, what is this? See, they told us this is 5 volts. So this is actually 502 pi t, and the phase is actually, because there's no phase, right? So it actually is plus 0. So if you want to change this to a phasor, you take 5, you take the angle of 0, so 5 at a phase of 0. So this is your phasor form. So you go back down here, you change it to a phasor, and then you divide by the Z total that we got. So the 1.00 plus 0.064 J, punch this in your calculator and you should get, so 5 at an angle of 0 divided by the Z total, we got this, but I want to change it to polar form. So in the end, I will get 4.98 at an angle of negative 3.66 degrees. Okay, so this is your phasor of I. What else? What will be the voltage across RL if the voltage source provides a constant voltage V naught across RL? Okay, so observe that all these nodes are the same. All these nodes are the same. And because of that, the voltage, see, the voltage difference across RL, right, given by the difference of the voltages across these two terminals, is the same as the voltage difference of Z para, the voltage difference across Z para. So if we can find the voltage difference across Z para, then we can find the voltage difference across ZRL because they're exactly the same. Okay, so how to find the voltage difference across ZRL of Z para? So we're gonna use potential divider. So potential divider will state that if you want to find the V across RL, which is actually the same as V. Okay, I'm going to state this explicitly. The V across RL is the same as the V across Z para. And we will find this using the potential divider. So this over the total multiplied by the voltage source. This is the voltage source. So Z para we got earlier was this, right? See, this is our Z para. So we're gonna chuck this in. Okay, this is our Z para divided by our Z total. Multiplied by V naught. So what you're gonna do is you're gonna key this into your calculator, okay? So let's key that into our calculator. This divided by, okay, what would be the voltage? Actually, I think you can honestly just leave it like this. It doesn't really matter to simplify or not. Oh wait, V naught they told us earlier, right? V naught, the value of V naught. Yeah. The value of V naught is 5. Sorry. So you sub in the value of 5 here. My bad. So this is actually 5. So I'm going to multiply my answer by 5. Then I'm going to change this to a phasor polar form. Ah, okay. So hang on a minute. What will the voltage? Constant voltage. You know what? I realize you cannot do this. You cannot do this. This is wrong. 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 Why? Because the voltage source is now constant, right? So what is this? The idea that we're supposed to buy it, the idea that we are supposed to apply is DC steady state. So first things first is you assume that is at DC steady state. So assume uh system has reached DC steady state. This means that you assume that the system has left to settle for a very long time. So no values are changing, no current is changing, no voltage is changing. So when things have reached DC steady state, right? Now what you're supposed to do is all the capacitors become open circuits. All inductors become short circuits. Okay? So let us refer back to this diagram. So when DC steady state is reached, we have to redraw this diagram. So this capacitor will be gone, and this inductor will become a short circuit. So in the end, our thing should look like this. Okay? So since this is an open circuit, we don't even need to draw it. Then this is a short circuit. The inductor becomes a short circuit. This is an open circuit. I don't need to draw it. Then the resistance, just keep it B. Ah, yes. Oh my God, this was a trick. Yeah, because I was thinking, it doesn't make sense to. Earlier, I was gonna do something wrong, and then I would obtain a phasor, right? But that doesn't make sense. You see, you're driven by a constant voltage, right? How can you suddenly get a AC output? That doesn't make sense. So actually, you're supposed to use DC steady state here. So all the capacitors become open circuits, meaning they're broken wires. All the inductors become short circuits, means they just become wires. This is R, this is RL, and then this is just the depth. And we still have a voltage source here, which is a value of V0, and V0 is just 5. Okay, so what are we supposed to find? Find the voltage difference across RL. Find the voltage difference across this. Okay. Actually, I think the voltage difference is across that is just 0. But let me try this. What if we did mesh current like this? Like this, like this. Just offhand, I think it's already 0. Let's try. So KVL at A. So let's start from here. We climb up. This is plus 5. And then we go through IA multiplied by R. What's the value of R? Oh yeah, it's 1 ohm. Then after going through R, we pass through this bare wire, then go back, then that means we've done it. This is finished. So this is equal to 0, right? So what does that mean? We can actually solve this already. So this 1 can go away. That means IA is equal to 5. Then um let's do a KVL at B. KVL at B. I think KVL at B will reveal something silly. So let us start from, let's say, here. Okay, we go through IB. We go through IB, that means minus IB times RL. And then after going through IB, there's no device, no device. So we reach the center again, the starting point. So this is 0. RL is something we don't care. That means IB equals to 0. Okay, so yeah, I'm correct. So right, you see, IB is equal to 0. How are we gonna find the potential difference across? See, we want to find this potential difference. So the potential difference across RL, right? So what we need to use is delta V equal to I times R. In this case, we use RL. Then we know that IB is equal to 0. There's no current flowing through here. So this is 0 times RL, which is just 0. Yeah, so this is the answer. This. Okay, so the voltage the voltage across RL is actually 0. Yeah, so this is the answer. So I think that's all. Yeah. Okay.